In this lecture, we will learn tricks to write Aldol product, be it addition or condensation. We will also learn to find reagents that form the particular Aldol product. For this, consider a reaction between benzaldehyde and acetone. Under basic conditions, an addition product is formed which we call Aldol addition product. Whereas at elevated temperatures, the same addition product gets dehydrated so as to form a condensation product, a dehydrated aldol. In this particular case, the former is a beta-hydroxy ketone, whereas the later is alpha-beta unsaturated ketone. Thus, to form this product, acetone has reacted as enolate and benzaldehyde as enolate acceptor. For our trick, find the alpha carbon of enolate, label carbonyl as C1 and alpha carbon as C2. The carbonyl of enolate acceptor as C3. Remember that, during aldol reaction, it is these three carbons that undergo bond breaking and bond making. So in the condensation product, you can spot these carbons here as 1, 2, 3, and likewise in addition product here as 1, 2, 3. To write the product directly without mechanism, write three carbons bonded to each other. Label these as 1, 2, 3. Always write carbonyl on C1. In case of aldol addition, always write hydroxy group on C3. The other groups attached with these three carbons in reagents can be connected accordingly in the product. For example, in this case, label methyl attached to C1 as C4. Connect C1 with methyl. C3 is connected to benzene. C2 has 2 and C3 has 1 hydrogen as in benzaldehyde. For aldol condensation, remove hydroxyl group from C3 and hydrogen from C2 and form a pi bond between C2-C3. Let us predict the major product, without writing mechanism, when this aldehyde is treated with aqueous sodium hydroxide. First, identify the alpha carbon. It has 2 hydrogens. Then, using our trick, label carbonyl as C1 and alpha carbon as C2. Write the same molecule in a way so that its carbonyl, labeled C3, is in line with C2. Connect C2 and C3 and change carbonyl at C3 into hydroxyl group. The other groups, connected with C1, 2, 3, are, as in the starting material. This gives addition product, a beta-hydroxyl carbonyl. Notice that carbon chains connected to C2 and C3 are facing opposite to each other. The other way to connect C2 and C3 is when carbon chains face on the same side. For this, write the molecule in blue so that C3 is in line with C2, as required for our trick, but carbon chain on C3 now faces towards left, as does the carbon chain on C2. Now, if the aldol addition product is subjected to heating, a water molecule is eliminated so that a pi bond is formed between C2 and C3. Similarly, in the other case, a water molecule is eliminated to form a pi bond between C2 and C3. This gives dehydrated aldol and alpha-beta unsaturated carbonyl. This is the trans isomer and this is the cis isomer. Normally the trans isomer is favored due to less steric interactions. Notice the carbon chain on C2 and C3 of the trans isomer having less interactions, whereas in case of cis isomer, the carbon chains face on same side and cause steric hindrance. Therefore, whenever two stereoisomers are possible, we draw the product that is likely to have less steric interactions. Consider this aldehyde subjected to heating in the presence of sodium hydroxide. This is self-Aldol reaction. To write the product without writing mechanism, first identify the alpha carbon. It has 2 hydrogens. Then using our trick, label carbonyl as C1 and alpha carbon as C2. Draw the same molecule, shown in blue color, in a way so that the carbonyl C3 is directly facing the alpha protons on C2. Also ensure the carbon chain on C3 faces opposite to that on C2. Remember C1 and C2 is to be labeled on enolate and C3 on enolate acceptor. Remove water molecule and connect C2 and C3 with a pi bond. Other groups are attached as in starting reagents. This gives the condensation product, a trans-stereoisomer preferably. Consider this ketone subjected to heating in the presence of sodium hydroxide. This is also self-Aldol reaction. To write the product without writing mechanism, first identify the alpha carbons. This is symmetrical ketone, so both alpha positions are same. Alpha carbon has 2 hydrogens. Then using our trick, label carbonyl as C1 and alpha carbon as C2. Draw the same molecule, shown in blue color, in a way so that the carbonyl at C3 is directly facing the alpha protons on C2. Remove water molecule and connect C2 and C3 with a double bond. Other groups are attached as in starting reagents. This gives the alpha-beta unsaturated ketone as condensation product. Consider the aldol reaction of this unsymmetrical ketone. With sodium hydroxide, this alpha carbon forms kinetic enolate, whereas this alpha carbon forms more stable thermodynamic enolate. With sodium hydroxide as base, the later dominates at equilibrium. To write the product without writing mechanism, using our shortcut method, write the ketone and label the carbonyl carbon as C1 and alpha carbon as C2. Then write the same molecule, shown in blue, so that C3 carbonyl directly faces the C2. Connect C2 and C3 and convert carbonyl at C3 into hydroxyl group. This is beta-hydroxyketone. The alpha carbon has no second hydrogen, therefore dehydration is not possible for this aldol product. Consider the reaction of 2-methylcyclohexanone with benzaldehyde in the presence of LDA base. The ketone has 2 types of alpha hydrogens, 2 on the right side and 1 on left side. Ketone is enolizable and aldehyde is non-enolizable. Recall that LDA preferentially gives kinetic enolate means less substituted. Using our trick to write the product, draw cyclohexanone and label carbonyl as C1 and alpha carbon as C2. Now draw benzaldehyde in a way so that carbonyl C3 is directly facing C2 alpha carbon of ketone. Connect C2 and C3 and convert C3 carbonyl into hydroxyl group. This gives beta-hydroxyketone as aldol product. Compare the product if the same reaction is carried in the presence of sodium hydroxide. Recall that sodium hydroxide gives more substituted thermodynamic enolate. To write the product using our shortcut method, draw methylcyclohexanone, label carbonyl as C1 and methyl substituted alpha carbon as C2. Draw benzaldehyde so that C3 carbonyl faces directly the C2 of ketone. Connect C2 with C3 and convert carbonyl at C3 into hydroxyl group. This is also beta-hydroxyketone product. Notice the position of methyl in both product. This is in presence of LDA and this in presence of sodium hydroxide. We can also use retrosynthetic approach to find the reagents that had formed a particular aldol product. Consider, for example, this aldol product. The first step is to identify alpha and beta positions. Using our trick, we can label the carbons as 1, 2, 3. So C2 is alpha and C3 is beta carbon. We know the bond between C2 and C3 is the bond formed during aldol reaction. Thus, during this aldol product formation, C2, which is alpha carbon, had reacted as nucleophile. Whereas C3, which is beta carbon, had reacted as electrophilic carbonyl carbon. Therefore, to draw the necessary starting materials, break apart the bond between the alpha, C2, and beta, C3, positions, restoring a carbonyl group in place of the OH group. This gives two starting compounds, a ketone and formaldehyde, clearly hinting this is a cross-aldol reaction. Remember that cross-aldol reactions must be directed, using LDA, if only one particular product is desired. In this case, ketone has two alpha carbons. The left one here has no hydrogen, therefore enolate is possible on right side only. The formaldehyde acts as enolate acceptor. As such, LDA is not required as base for this aldol addition. Sodium hydroxide can be used as shown. Let us identify the reagents needed to produce this aldol reaction product. First, we identify alpha and beta positions. This is beta hydroxyketone, an aldol addition product. Using our trick, we can identify the three carbons and label these carbons as 1, 2, 3. So that C2 is alpha and C3 is beta carbon in the product. We will then apply retrosynthetic approach. That means break apart the bond between the alpha, C2, and beta, C3, positions, and restoring a carbonyl group in place of the OH group. This gives two starting compounds, a ketone and an aldehyde, clearly hinting this is a cross-aldol reaction. Notice that aldehyde is non-enolizable, therefore it cannot undergo self-condensation. Thus LDA is not needed to direct this aldol reaction. Sodium hydroxide can be used. Thus we can use our trick to join these reagents. Label ketone carbonyl as C1 and alpha carbon C2. The aldehyde carbonyl carbon as C3. We can join C2 and C3 and convert C3 carbonyl into OH group. Thus ketone forms enolate in the presence of sodium hydroxide and aldehyde acts as enolate acceptor. This is simple cross-aldol addition reaction. Let us identify the reagents needed to produce this aldol reaction product. Begin by identifying the alpha and beta positions. Now apply a retrosynthetic analysis. The bond between the alpha and beta positions is the bond formed during an aldol reaction. To draw the necessary starting materials, break apart the bond between the alpha and beta positions, restoring a carbonyl group in place of the OH group. This gives two starting carbonyl compounds. This part has acted as enolate and this as enolate acceptor. This is ketone and this is aldehyde, so a cross-aldol reaction is required. But the aldehyde also has alpha hydrogens and can form enolate under basic conditions and form mixture of products. So sodium hydroxide base cannot be used because it would result in a mixture of four products. To avoid the mixture and get only one major product is possible via directed crossed aldol reaction. This can be accomplished if LDA is used as base. In the first step, the symmetrical ketone is irreversibly and completely deprotonated by LDA to produce a solution of enolate ions. Then, the aldehyde is added dropwise to the solution to achieve a directed aldol addition, which will give the desired product as the only major product. Likewise, to identify the reagents needed to produce this condensation product. Begin as usual by identifying the alpha and beta carbons. Then apply retrosynthetic approach to identify the starting materials. Break the bond between alpha and beta carbon. This gives a cyclic ketone and an aldehyde. Using our trick, we can identify and label the carbons in these as 1, 2, 3. The aldehyde is clearly non-enolizable and can only act as enolate acceptor, whereas cyclic ketone forms the enolate. This hints about cross-aldol condensation. Thus LDA base is not needed to direct this aldol condensation. Sodium hydroxide base can be used. Again, using our trick, we can write the starting materials so that oxygen is between C2 and C3. Then remove a water molecule to form double bond between C2 and C3. This is the desired cross-aldol condensation product. To identify the reagents needed to produce this aldol addition product. Identify the alpha and beta carbon. Then apply retrosynthetic approach to identify the starting materials. Break the bond between alpha and beta carbon. This gives a ketone which has reacted as enolate and an aldehyde, acetaldehyde, which has reacted as enolate acceptor. But acetaldehyde is also enolizable under basic conditions and can also form enolate to give mixture of products. Therefore, to avoid self-condensation of aldehyde and give only the desired cross-product. This cross-aldol condensation must be directed using LDA base. In the first step, the ketone is irreversibly and completely deprotonated by LDA to produce a solution of enolate ions. Then, the aldehyde is added dropwise to the solution to achieve a directed aldol addition, which will give the desired product as the only major product. Remember the trick of labeling carbons to form aldol product. The enolate carbonyl as C1, alpha carbon C2, and the carbonyl of enolate acceptor as C3. Joining C2 and C3 and changing carbonyl at C3 to hydroxyl group for addition reaction. Similarly, to identify the reagents needed to produce this aldol addition product. Identify the alpha and beta carbon. Then break the bond between alpha and beta carbon. This gives ketone 1, cyclohexanone, which has reacted as enolate, and ketone 2, which has reacted as enolate acceptor. Thus, this is cross-condensation between two ketones. But ketone 2 is also enolizable under basic conditions and mixture of products is possible. Therefore, to avoid mixture of products and give only the desired cross-product. This cross-aldol condensation must be directed using LDA base. In the first step, the ketone 1 is irreversibly and completely deprotonated by LDA to produce a solution of enolate ions. Then, the ketone 2 is added dropwise to the solution to achieve a directed aldol addition, which will give the desired product as the only major product. Using our trick of labeling carbons The enolate carbonyl of ketone 1 is C1, alpha carbon C2, and the carbonyl of enolate acceptor, ketone 2, as C3. Joining C2 and C3 and changing carbonyl at C3 to hydroxyl group for addition reaction. The other groups are attached to labeled carbons as in reagents.